Welcome back to our course with one more lecture. As you remember from last lecture, we were looking to the wave aspect of particles, right? We call that normally matter waves, right? So we understood that the nature is telling us that in many circumstances, particles that normally we associate with energy and momentum, it's better described by frequency and wavelength, which is waves. So what we learned on the last few lectures is that to really understand the many aspects of what we see, we gotta have this duality wave-particle. And we start by going in this direction. We start by looking to waves, which is the electromagnetic wave from the radiation that comes from heated bodies, and we observe the particle behavior. That was the beginning of the photons, or particles of light. And then we prove the opposite. With the help of de Broglie convince us that there should be a reciprocity and particles should also behave like waves. So the connection between momentum and wavelength and frequency and energy is given by those relations, and we now can go in both ways. So we now can navigate having waves behaving like particles and having particles behaving like waves. We're gonna focus now on the particles, right? Because we have particles, and then we're gonna associate with that waves. And I keep putting the question for you: waves of what, right? Because electromagnetic are waves of electrical and magnetic fields, but matter, mass, they are waves of what? And normally we gotta deal with this. We have to understand that when we take up anything and we associate with a plane wave, you know, particles normally are localized in space. That's why we can speak about trajectories. And waves, when we associate with a plane wave, they are delocalized. They are everywhere in space. We normally put this kind of function, sine type or cosine type, and we let it go for the whole space and time, right? And that creates a few problems to us, because we normally are, in your view, particles are localized. We can see particles, and then we're going to explore a little bit this now in this lecture. Okay, well, if we're going to have to associate with a particle, a wave of frequency and a wavelength, it's better to associate with a plane wave, right? In a first approach, we have a particle, right? Normally particles are described by trajectories, and waves are described by wave function that normally we're going to call psi. So psi for us is the one of the main functions that we use in quantum mechanics. And by the way, quantum mechanics is also called wave mechanics. Because of this, we're going to deal with mass, but now in a wave context. Okay. So we're going to follow de Broglie, and we're going to take a particle that has some momentum and energy, and we're going to associate with a wave of frequency and wavelength. So associating with this, a plane wave, we're going to connect a particle with momentum and energy with a wave. And that's the wave function we're going to associate with. And of course, we have to learn how to extract from this wave the properties we want. And we're going to do that bit by bit. The first thing we can see here is that You know, this is the first choice for a wave function. Because I have a frequency, I have a lambda. This is the best I can do, right? It's putting a running wave with frequency nu and with spatial periodicity lambda. And normally this is written as a cosine or sine. I choose a cosine this time. An amplitude, 2 pi, and cosines of 2 pi nu t minus 2 pi x over lambda. So lambda gives you the periodicity in space and nu the periodicity in time. And the first thing we can get here is, suppose that I want this amplitude. This is oscillating in time and space. But then I say, well, I want to follow in time and space. This is a running wave, a fixed amplitude. So I say, well, let's sit on the maximum of this wave. So let's sit on the maximum of the wave. If we put ourselves on the maximum of the wave, it's like saying that the argument of this cosine is 0. And if its cosine is 0, I can get x over t, which will be nu times lambda. And x over t, of course, is how the space developed with time. And this is velocity. And if I put on lambda, I put the relation of de Broglie, which is h divided by mv. And in nu, I put the energy divided by the best. I put the energy. You know, if you have a particle, you can. This is not fully true, but I can associate with half mv squared divided by h. And then when I take everything out, I found that this wave is not really moving with the velocity of the particle. You know, it's half of it, but that doesn't matter. I just want to show that there is a problem here. When we have a particle and we are associating this particle traveling with some velocity, just associating a plane wave doesn't help. So we expected that whatever is the wave associated with the particle will propagate in space with the velocity of the particle. And this is very different. We can improve a little bit this calculation, right? Because we know that for electromagnetic wave for phonons, that should work well. So let's consider improving this calculation. Okay, so improving this calculation, we want to take not the energy as a half of mv squared, but using the relativistic relation, which is mc squared. And we're going to say that mc squared, which is general, it works for any velocity because the mass, as you may remember, is a mass of resting mass divided by root square of 1 minus, right? This mass is equal to resting mass divided by root square of 1 minus v square of c square. And then we can prove that this energy goes to half mv squared when we want, and so on. Anyway, let's improve this, putting that way. And lambda, of course, is the h divided by the momentum. And then from here now, we can calculate the de Broglie wave propagation. And we get c squared divided by v. That's even worse coincidence, because we know that the particle cannot go. This is always bigger than c and is equal to c when we are dealing with photons. If we're dealing with photons, the v is c, so this gives c. In the case of electromagnetic waves, photons are behaving well. Photons are propagating particles in this context, propagating with the velocity that should, which is c. But we are dealing with a particle that is propagating with velocity v. And therefore, we are getting here an inconsistency, because we are getting a de Broglie wave propagating with velocity bigger than c. And they are not equal. We are looking for a particle and a wave that has some relation on the propagation. And I will explain why. Okay, and this is, I already told you, if you are dealing with photons, then it's fine. Because we are dealing with V that's equal to C. The mass is 0, but we already cancel that later, right, before. Okay, so this is then we have a point here to be made. The wave with lambda and nu is everywhere in space. It is fully delocalized. And we know that if you are associating to the particle a wave, whatever we have wave, we have particle, right? I mean, the particle is now the wave occupying some space. You see that we are dealing basically with a free particle traveling, and that's the reason why we associate with a plane free wave propagating. So we should know that where there is particle is there wave, and where there is wave, there is particle. But the wave that we associate with this particle is everywhere in space. And it cannot be. A particle cannot be everywhere. Well, eventually it can, but it's not the case for many of the experiments we do. We know that the electron is in the atom, is there in the atom. It's not equally everywhere in the universe. So, because of this wave that we associate is everywhere in space, it means that we have to improve this wave associated with the particle with velocity v. It cannot be. We cannot really take this. If we take, we pay a very high cost, which is, we don't know where's the particle. It's everywhere. And normally that's not the physical situation. But, you know, if we're dealing with electron or electron traveling from a discharge, or an electron that is obtained from ionization or from the electron, from the photoelectron effect, we know that it travels with some velocity and reaches the detector. We can measure that. So we have to improve this association of the wave with the particle that in a first approach we took a free running wave, but we have to improve that to see if we can solve this problem of the localization. Because we know that if I throw a particle, if the particle is like a wave, the wave has to be traveling with the particle with the same velocity. So to do that, we must improve this situation. Let's do first an experiment. We're going to do an experiment of photoionization. So we're going to do a photoionization or a photoelectric effect. So what we want to do is create the physical situation where we have something ejecting an electron, and that can be the photoelectron effect, right? So we eject the electron, and then we make a detection system, right? We have a detector, so that we're going to measure a current. We know that the electrons are flowing, right? But what we're going to do is put a grid here and a grid here. And always that the electron pass, there is an induction, and I see a little peak. And whatever passes here on this grid, I see another peak. And if I eject an electron, and I have this system running, and of course I have to apply a voltage between the grids and everything, what I see is two clicks. One click when the electron passes to the first position, and a second click when the electron passes to the second position. There is a time of fly between the two grids. And if there is a time of fly, means that there is a velocity. This distance divided by this time is the velocity. And this is velocity of what? Velocity of the electron. But the electron is a wave, it should be everywhere. But I'm seeing that the electron passes here and later on passes here. So I hope you understand that because of this electron has a moment where it passes to the first grid and then the second grid. It cannot be a plane wave, because a plane wave will be everywhere at the same time. So it has to be a wave that's more localized. in a way that when the wave is passing here, I detect the electron here. And when it's here, I detect it here. Otherwise, I cannot really associate this wave for this particle. Okay? Okay, well, then the second thing that's more reasonable to imagine is that the electron actually is a wave pack. If you don't remember from the fundamentals of wave mechanics and everything that we learned in high school and then in the early courses in the engineering course, right? A plane wave is like this, but a wave packet, the wave actually localizes. It has a kind of envelope that makes the envelope as a whole propagates with some velocity, right? And the way to make a wave packet will be a better description of this particle than a plane wave, I think, right? Of course, the package can be very big or can be very small. That's depend. You know, this clique is not exactly delta function. They are broad in some sense, but we needed to convert the plane wave associated with this particle with a wave packet, which is how you make a wave packet, right? To make a wave packet, we use a sum of plane waves. But how we make the wave packet? Well, we can make a wave packet if we add waves of different wavelengths and different frequencies, therefore. So by adding waves of different frequency and wavelength, we can create this modulation. And if we add enough in a range, we can create the wave packet. This is a well-established concept in wave mechanics in general, classical waves, right? That you can make a package. Like the wave in an ocean, they don't come like this, you know. You see a wave that goes in a package propagating. Probably that wave, in terms of wave in the water, will have a lot of different frequencies and different wavelengths. So, to make a package, this is the question, right? Let's make a package to localize this wave, more or less trying to catch the concept that a particle maybe is more localized in space than a plane wave. So let's add wave. I'm going to change a little bit the notation now. And I'm going to introduce omega for the frequency, because then we don't need to carry on in all the things, the 2 pi. But 2 pi times the frequency is omega. Omega is a frequency that is expressed in radians, in angle, right, per unit of time, which is the better way to use it, because we're going to use it basically trigonometric function. And trigonometric function, in the argument, we need angles, not time or inverse time or centimeters or anything like this. So this is good. Another thing that's good is that instead of lambda, we're going to use the wave vector, which is k. K is 2 pi divided by lambda. So if you look to the expression we had to the plane wave before, instead of 2 pi over lambda, we're going to have k. Instead of 2 pi times nu, we're going to have omega. And we're going to start this exercise by putting a one plane wave of frequency omega and wave number k. And then another one that differs from the first by delta omega and by delta k. So the frequency of the second wave is slightly different from the first. By a small quantity. We are dealing with small quantities. We want to have small quantities for delta omega and for delta k. How many waves we have in this interval? Now we're going to start with 2 waves, and then we're going to generalize. Now let's add up the two waves. We're gonna put together these two waves. You know when we add up cosines, because this will be the cosines of one wave that has omega k and another one that has omega plus delta omega and k plus delta k. And you remember that in high school, when we have cosinus of A plus cosinus of B, this is equal to cosinus of 2 times cosinus of A plus B divided by 2, A minus B divided by 2. I'm going to apply this trigonometric relation for adding cosines. When I do that, when I add this term with this and divide it by 2, of course, because the delta omega is small and delta k is small, I take that out, and I end by having basically, I'm going to have 2 omega divided by 2 is just omega, and 2k divided by 2, that's just k. So I have the first term. Now, when I subtract the two arguments, only the delta will survive. Only the difference between the frequency and the wave number of the two waves will survive. And then I have this term here, which is delta omega divided by 2 and delta k divided by 2. So this is like a wave of much lower frequency because delta omega is much smaller than omega. And delta k smaller compared with k. We use this relation here. So what I want to say is this is a tiny difference on k here. Right? Which does not mean that lambda k is the inverse of lambda, but we don't need to worry about these details now. It turns out that the addition of these two waves is this expression. So when I add the two waves with a slight different frequency and wavelength or wave number here, I get a modulation. So the wave that was continuous everywhere now bunches in packages. We have a fast oscillation, and if you look here in this expression, the fast oscillation is this term. And the velocity that this propagate is x divided by t, which is omega divided by k. This is the velocity of the fast oscillation. And we have a slow oscillation, which is given by this low frequency. And the frequency that this package moves, inside the package, the wave is moving fast. But on the package, the wave is moving slowly, because now what I have is delta omega divided by delta k as x divided by t. So this slow part comes with a wave, and this, because this looks like a wave package, or we call group, right? A bunch of waves that is inside this envelope. The envelope itself propagates with this group velocity, which we call V group. And inside, the wave may be propagating fast, but doesn't matter. The whole package is going that way, and then there are points that are zero here propagating together. So somehow, by putting more than one wave of different frequency and different wavelength, we collapse the wave in lobes, which is more localized than just a plane wave. Right? We add two waves, but imagine that I say to you that in between omega and omega plus delta omega, we have many waves. We can put many waves, tiny spaced in between, and then add up. I tell you what's going to happen. This modulation is because here there is a destructive interference, and here there is a constructive interference. That's why the total amplitude is 2A, and is 0 here. Those nodes, they come because the conjugation of these two differences comes to be a destructive interference here and a constructive interference here on the top. If I add more waves within the interval delta omega, I'm going to have many waves that just have a constructive interference. They add up in a region and subtract everywhere else. So I can, by adding more waves, diminish the number of those lobes, of those modulations, and end up with a single one. Well, this has to be done with a kind of integral, because now I'm going to consider that I have infinite waves between omega and omega plus delta omega. And this is basically what I'm doing here. I am just, we just add two waves and see that this somehow creates this envelope that localizes the wave, but still many localization. Now, if we consider many waves in an interval delta k and delta omega, I'm adding many waves. I guarantee to you that they all added together, giving a constructive interference in one point, in one region, and destructive interference everywhere. So what's happened then is that this wave is like a package which oscillation exists in a narrow region. Somehow we localize this wave. The wave is now localized here. And localize it in some distance that I'm going to call delta x. That looks like more a particle. Because if we have a particle, it is localized. When I throw a, remember many classes, many lectures ago, I calculate what should be the wavelength of a tennis ball. And we come with an absurd small number. And then we say, well, how can we see some wave behavior with such a small wavelength? And the reason, and then I say, yeah, we cannot. Right? We cannot. But we know that the tennis ball is localized in this region because the lambda here, because delta k is small or delta omega is small, the lambda is around. The lambda that we have is around h over mv. It's around this. But now, with many additions to one side and many additions to the other. So, what we are saying is that the best way to represent a particle is not by a single wave, it's by many waves which wavelength is around the de Broglie wavelength. And that creates a localization which is more like particle. But it's wave, because it's a wave packet, or a localization of the wave. We still have a fast component, which is this. And if we look around, you do the calculation, we're going to get that this fast velocity, fast wave propagating, is propagating with c squared divided by v, which is what we call the phase velocity. It's bigger than the velocity of light. But that doesn't matter, because this is not what characterizes the physical situation. What characterizes the physical situation, which is this wave packet represents the particle, is the slow part. And the slow part has a group velocity. And this group velocity, if we calculate, is exactly the velocity of the particle. It's exactly the velocity that comes here in the very beginning. So, when I have the electron going, what I have around it, this is like a package of wave coming. And this localization gives the click that I did in the experiment before. Now, we needed to observe that to localize the wave that represents the particle, we have to add many wavelengths of tiny little different values and many frequencies. Which means by adding tiny little different values of lambda, it's like having an uncertainty on the momentum of the particle. Means that the momentum of the particle is within a range that I'm going to call delta P. Delta P represents delta lambda or delta K, is the same. And delta X as well is a localization in space, because now the particle is localized in a range of space. It's not everywhere in space, because here is zero. The amplitude of the wave packet is zero. The wave exists only here. Out of this range, the oscillatory behavior is gone. And equivalent, we can speak about the energy and the time, as I'm going to show to you now. Okay, so as a consequence of this, we can calculate what is the wavelength when we add those. I already showed to you that the wavelength of this modulation is 2 pi divided by half of delta K, which is this, right? The wavelength of this modulation that we have here is basically 2 pi divided by this number. Right? Okay, and delta X is half of this wave. If I take this oscillation as a wave, this envelope as a one wave, we can associate with it the delocalization, which is half of this modulation wavelength. Okay, so if I just do some calculation, I hope this is not heavy calculation, I can associate the slow part with a modulation wavelength, which is this, is the inverse of that term. And this is the size of the wave package, right? So basically, the size of the wave packet is this, right? Is this 2 pi divided by delta K, because it's half of the wavelength. But we know that K is equal to 2 pi divided by hp, or delta K means a delta P. And the inverse of delta K is delta X. So this is the inverse. At the end of the day, there is a relation of how many momentum, what's the variation of the momentum, how many momentums we have to add, and the localization or the delocalization that we add up. And this is, the product of this is about Planck's constant. Okay, so what is the take-home message here for this part? Well, the take-home message for this part is that to localize the wave, we have to add waves of tiny little different wavelengths in a range. And that means that we have an imprecision on momentum and an imprecision in position. It's not everywhere, it's localized, but it's not a single momentum anymore. In other words, we can say that localization of the particle, or the wave that represents the particle, implies an imprecision on the momentum. And this is the Heisenberg principle, or uncertainty principle, that we learn in school. And the reason is that the wave nature is in the particle. Therefore, if I can localize the particle, means that many momentum was added to localize this wave packet. So you don't know exactly what's the momentum. The momentum can be anything in between. And because I don't know exactly, I add up everything, and that turns to be the imprecision in the momentum. The localization of the particle and the imprecision in the momentum has consequences in quantum mechanics that goes much beyond what we think. And we're going to restart next lecture in this topic, exactly from this point that we are ending now, to show you the consequences of localizing particles, because we cannot give a de Broglie plane wave to the particle. We have to localize. And that has consequences in energy, in momentum, in everything. And that's what we're going to see in the next lecture. See you then.